So this lecture is on blood types, clotting, and white blood cells, leukocytes. And so what we're going to see today is the different blood types. We talked about this in lab a lot. Um, Over here, first of all, we need to know what an antigen is. An antigen is a little glycoprotein, meaning it's a glyco sugar protein. It's a fusion of a protein with a little piece of carbohydrate. And actually, antigens are found on most things. So, most of our cells, most bacteria, most viruses have little antigens on them, little markers on their surface. They're just little markers on the surface. And specifically, we'll be talking about surface antigens on red blood cells, on erythrocytes. So these little antigens, they're genetically determined. So we get that from our genetics, right? And they act as ID markers. They're kind of like saying, hey, this is who I am, right? So it allows the immune system to determine what are our cells. So our immune system goes around scouting for things that are non-self, things that are foreign to our own body, and then it'll attack it. So we want our cells to be able to say, "Hey, I belong to your body. I'm good," right? And so our bodies, the way our genetics is will give us our blood type is that we have only one blood type, right? So we have one configuration of these ID markers. So the antigens, right? Your blood type is determined by three different markers, three different antigens. The first that we'll talk about is the ABO blood group. Either you could have some A antigens, right? So if you see these red little specks, that means that you have A antigens on all of your red blood cells. You could have B antigens, right? You see some of these have these little blue arrows. That means that you have B antigens on all of your red blood cells. Interestingly, you could also have Rh antigens. So the rhesus group, right? You could have these green little antigens, then you'd have the Rh antigen. Now, look at all of these possible combinations, right? Your body only has one of these types. You are only A positive or you are only O negative. You do not have a mix of all of these. You just have one of them because it's genetically determined from your mother and father. So, I want us to look at the blood types. You could be A positive, right? Um, so again, the ABO, you will just write the letter that is there, whereas the RH is determined by the little plus sign or the negative sign. So actually, not to confuse us, I'm going to start with the RH negative ones. So if I am A minus, I only have A antigens. If I am B minus, I only have B antigens. If I am AB minus, I only have A and B antigens. And if I have O minus, then I have zero antigens. So I do not have A or B. Now, the RH group, the way that we indicate if you have RH or not is by the little plus or the minus sign. So if you do not have the RH antigen, then it's RH negative, right? So all of these are negative because look, none of them have the green antigen on the top, on their surface. And then if you're Rh positive, look at all of these. They all have the green antigen. So they are positive for the Rh. So if you're A or B, that you will write the letter A, B, or AB, or O for zero if you have none of them. If you have RH or not, you will put a little plus or a little minus above the letters, right? That's how you will tell. So you are only one of these blood types, right? And someone else might be a different blood type, but they are just one of these, right? Um, why is blood type important? Because, as I told you, the immune system, your immune system, attacks non-self antigens, right? Because they think that it's dangerous. It doesn't belong to you, so it will attack it. So, during an incorrect blood transfusion, your immune system's antibodies, right, will attack foreign red blood cells that have the incompatible antigens. Let's see, for example, here. Here you have some red blood cells, right, of the donor, right? The donor, you only give, this is actually key. Um, when you give red bloods, you give a blood donation, right? They will take, yes, they will take your whole blood, but then they will actually just take out the red blood cells. And when they donate it to someone else, right, they will just give the packed red blood cells. They just will give the red blood cells to the patient that needs it. That avoids giving the antibodies to the person that's getting the donation, right? You don't want to give the donors the the you don't want to give their antibodies to them, right? So, for example, over here, the donor's red blood cells, they have B antigens. They do not have A antigens on their red blood cells, okay? The patient, right, has plasma with B antibodies. So this is the patient who's dying in the hospital, and this is the transfusion that's being given to the patient. And as you see, we won't discuss yet what the patient's blood type is, but the patient has B antibodies in their blood already, ready to attack any donation that has B antigens. So if you donate these red blood cells, what happens is these anti-B antibodies will bind onto the red blood cells over here. Do you see how they're binding onto the antigen? Because antibodies recognize antigens on red blood cells. So you will see what we call agglutination. The red blood cells will agglutinate and clump together because of the antibodies sticking them together. And then what's going to happen again is they will recruit the other immune system cells to destroy and hemolyze the red blood cells. Antibodies are basically the fighters of the cell. Remember, for COVID, we make antibodies to go and attack the virus, right? So the whole point of a vaccine is to make antibodies to then be ready to attack the virus. So same situation here. These antibodies, if they are exposed to bad blood, right, that has that antigen, they would attack it and they would agglutinate and hemolyze the red blood cells. Hemo means blood, lysis means to chop up, right? So basically, an incorrect blood transfusion, this is an incorrect transfusion. This is the donor and this is the patient receiving the blood. They are not compatible because you saw that these antibodies could bind onto these receptors that were the B antigens. And so when you get an incorrect blood transfusion, antibody antigen binding occurs and agglutination occurs. Red blood cells will clump together and hemolysis will occur. The red blood cells will get ripped apart. So, let's take a look at how blood type determines the types of antibodies that you produce. The rule of thumb is that your immune system makes antibodies against what you don't have. It wouldn't make sense that you have antibodies against things that you already have in your body, or else this is called an autoimmune disease. You attack your own body. So if you are type A blood, that means that your little red blood cells have a surface antigen that is A. You do not have antibodies for the A antigens, right? If you have type A blood, your plasma contains anti-B, right? So they're showing it in blue here, which will only attack type B surface antigens, right? These antibodies do not bind onto these antigens. They don't match, right? These antibodies are the anti-B antibodies. Type B, if you are type B, right, your blood has red blood cells with surface antigen B, right? Do you see how there's this surface antigen over here? That's the B. If you have type B blood, you do not have these guys. These were anti-B antibodies, right? These are anti-A antibodies. So it makes sense to have these antibodies, right? They will not attack your antigen that is B, okay? These only would attack antigen A if there was a transfusion, right? Type AB blood has red blood cells with both A and B, right? So if you're type AB, you have A antigen and you have B antigen, and you do not have any antibodies, right? Because if you had anti-A, they would attack the A antigen. If you had anti-B, they would attack the B antigen. And lastly, if you're type O, your blood has 0 antigens, right? You don't have any antigens. And again, remember our rule. Your immune system makes antibodies against what you don't have. You don't have anything. So you will make antibodies against type B and against type A. So you have anti-B and anti-A antibodies, okay? So again, I remind you, you make antibodies against what you don't have. I have A, so I will make antibodies against B. I have B, so I make antibodies against A. I have A and B, so my body will not make any antibodies since I don't want to attack myself, right? And here I have no antigens, so I will have antibodies against everything. That's how the ABO system works. Now, I warn you, this is tricky. The Rh factor, the rhesus factor, when you are positive, right? So this was just AB or O, right? But remember, there's usually a plus or a minus. If you're positive, that means that you are positive for the Rh antigen. Rh positive means that you have this on your membrane. And if you have this on your membrane, right, these little Rh positives, this means that your plasma does not have any anti-Rh, right? This makes sense. You have your Rh antigen, so you would not make antibodies against it, okay? Here's where shit hits the fan. If you are Rh negative, meaning you do not have any antibodies, right? Unlike the ABO system, okay, Rh negative people do not naturally have anti-Rh. So over here, right, let's say you're O, you will have A and B antibodies naturally at birth, right? If you are B, you will naturally have A. But for Rh, it's a bit different. Rh negative people do not have anti-Rh antibodies, right? Normally we would think that according to this system, if you are Rh negative, then you would have these antibodies ready to attack if it saw it. But actually, they only develop the antibodies after exposure to Rh positive blood. So only after there's one exposure would they develop the antibodies. And I'll tell you why that is. Like this actually makes the most sense to me because it's kind of like a COVID or a bacteria, right? When you get exposed to COVID, let's say you hadn't gotten vaccinated yet and you got COVID, your body will see that foreign virus and it will make antibodies to try to fight it, right? So you never had the antibody to COVID unless you were vaccinated before. Um, but let's say at the beginning of the COVID wave, right, when we didn't have a vaccine, you were never exposed to COVID, so you never had the antibody. And then all of a sudden, if ever you got the virus, right, you would make the antibodies against it. That's how the Rh negative works. If ever this person is exposed to it, then their immune system will be primed and they will, let me go draw it, they will go make the little antibodies, the anti-Rh, right? But only after the exposure, at the first exposure. Whereas in this system, ABO, you are born with it, right? You've never seen B blood, but you have anti-B. Let me go write it. You have these anti-B antibodies, okay? Anti-B. And over here, right, you've never been exposed to to the antigen of A, right? But you do already have primed anti-A antibodies, okay? So they're ready to go. Um, One last thing I just maybe forgot to situate us in a blood vessel, right? Remember we said that there are cells, right? There's these red blood cells, and they have their little receptors on top, right? Those are the antigens that are on top of the red blood cell. But I think people have difficulty sometimes understanding that the the antibodies, right? They are also floating in the plasma, right? These antibodies are floating in the plasma, but they're not in the red blood cell, right? They're just floating in the plasma of the blood. And I say this because when you donate blood, right, you actually remove all this plasma and you only donate the red blood cell, which will be important for us when we start talking about um, donations. Okay, so here's a problem to try. The death of a teacher. An annoying teacher named Sam could not shut up about cellular respiration. Therefore, someone on the street murders him in the middle of the night, and the killer's blood is found on the crime scene. It's one of his students for sure. The investigators find the following. So here's what we find. Let's go. I'll give you, maybe pause the video and try to take a crack at it first on your own. All right, so here's my red blood cell, right? I want us to draw what we have first of all. So we have B antigens, right? So we have little B antigens all over here. B, right? We have anti-A antibodies. So I'll put that in red. Here's anti-A. And we have Rh antigens present. So let's put that in green here. We have Rh found on the surface. We have Rh found on the surface. So I just want to make sure we understand the whole picture of this. Would we have anti-Rh? No, right? We would not have anti-Rh because Rh is an antigen. You would not have something to attack yourself. Would we have anti-B antibodies? No, because you would not have those antibodies to attack yourself. You have B antigens, so they would not attack your own, and you would not have antibodies to attack your own antigens, right? So now that we've clarified everything, let's state what the blood type is here. So the blood type on the red blood cell, I see that there is B, right? I don't see A, and I see RH. And for RH, remember we put a positive if it's there and we put a negative if it's not. So this suspect is B positive. Um, and then the follow-up is the stolen painting has fingertips that match a person with type AB blood. Could this be the same person? Why or why not? So over here, right, AB, let's go see what AB would look like. If I am AB, right, what does that mean? And I didn't even say if it's positive or negative. I just want us to draw AB. If it's AB, then that means that there's A surface antigens, and on top of it there is B surface antigens, right? So it could not be the same person because this patient, right, this person, suspect, has, yes, they have B, just like this one, but this person has A, and this person does not have A. So it could not be that person. We would exclude them from our who we think they are. Okay? Perfect. Next, a suspect at a bank heist leaves behind drops of blood. Forensics find the following. What is the blood type of the patient? So go and pause the video. So what is their blood type? A and B antigens are found. So A is here, right? A. We have B antigens, B and B, right? No antibodies are present, interesting, and RH antigens are present. So RH. And I'll put another one here, RH. And there's no antigens present. Sorry, there's no antibodies present. Does that make sense? Yes. We wouldn't have any antibodies against our own. And we have every antigen under the sun. So we have no antibodies that would attack our own red blood cells. So no antibodies, right? No antibodies present. No antibodies present. Usually I put my list of antibodies here and I have none, right? So there's none here. Okay, so what is the blood type? I have some A, I have some B, and I have some RH. How do I write RH? I put a positive here. So this patient would be AB positive, right? Could this suspect safely receive blood from someone with type O negative? Why or why not? Here's my red blood cell, right? O negative. Okay. Oof. What does O negative mean? O negative means I have 0. I do not have A or B. The negative means that I do not have the RH factor, right? So there's absolutely 0. There's 0 A or B, and there's negative. There's no RH, right? So I want you to tell me about the antibodies. What kind of antibodies would I have, right? I would have anti-A, anti-A. I would have anti-B, right? Anti-B. And would I have, here's our crazy discussion here. Would I have anti-RH? It depends, right? If you've never been exposed to RH positive blood, then you would not have anti-RH, which is the most likely case. The only time you would be exposed to anti-RH blood is if you're a mother and the fetus was RH positive and there was hemorrhaging and mixing of the blood. That's the only really time that would happen. So actually, you do not have anti-Rh blood. Okay? So I'm not even going to put it here. There's none of these antibodies that would be present. So could this suspect safely receive blood? Can I transfuse this blood to this patient over here, right? Over here, when you do a blood transfusion, it's important to note that only the red blood cells, right, are going to be sent to the patient. We do not send the antibodies to the patient. We only send the red blood cells, right? We isolate red blood cells and we send it to the patient. So this red blood cell has no danger signal, right? That would be on it, that would be bad. So actually we're totally fine, right? We're okay with sending this O negative blood to AB positive. You know why? Because first of all, AB positive, they are universal recipients. They can receive from whoever. You know why? Because they have no antibodies that would attack any type of blood. And you know what? O negative blood is a universal donor because it has no antigens on its surface. So no matter who is given this blood, right, then they will not react to anything on their surface, right? The recipient will not have any any problem. There's no red flags on their surface at all. However, if you did the opposite, right, then that's a problem, right? If you gave AB positive to this patient, if you actually gave this blood to this patient, look, this patient has anti-A, anti-B, they would attack this red blood cell. And if you gave the opposite, right? Sorry, yeah. So that was the scenario I wanted to show. Okay, I think we're good with that. Now, over here, blood samples in a car accident. We had a mix of blood, and so investigators determine sample 1 has this stuff. Sample 2 has only the B antigens and Rh antigens. What is the blood type of the 2 individuals? So pause the video. Alrighty, so here for sample 1, we only have A antigens, no Rh antigen present. For sample 2, we have only B antigens and Rh antigens are present. Rh. Okay, so over here, let's go draw out what we would have as, well, let's actually go tell ourselves what the blood type is here, right? It would be A negative, right? Because we have A, we do not have B, and we have no Rh. So that's the negative. No Rh is the negative. Here we would have no A, we would have B, and we do have Rh, so this would be B positive. Now, what are my antibodies? I do not have anti-A because I have A antigen. I do have anti-B. So here's my little antibody over here, anti-B. And I would not have anti-Rh unless I get exposed to blood that is Rh positive. Over here, right, I do have anti-A. I do not have anti-B. I do not have anti-RH. Okay, so here is my little anti-A. If one individual needs a blood transfusion, would they safely donate to the other? Explain. Let's go see. If I donate this blood, right? Remember, I don't donate the antibodies. If I donate this blood to this patient, right? Then they have anti-A. This antibody would bind onto A, and it would hemolyze and break apart, rip apart the red blood cell. That's not good. Let's try the other way around, okay? So let's go the other way. If I took this blood here and I donated it to this patient, remember, I do not donate this anti-A. If I donate this blood to this patient, their anti-B, right, would bind onto the B antigens and would rip it apart, right, and it would hemolyze it. So that would not be good. So the answer is no. They're not compatible because they each have the opposite antibodies that would attack. Okay. All right. So you know the RH whole disaster. I want to explain why that's a problem. So hemolytic disease of the newborn. This is why the RH situation is a bit weird. An RH negative mother, an RH negative mother. So here you see this mom is RH negative, does not have an antibody against RH antigen, right? Remember, they do not make this RH antibody yet unless they're exposed to it, right? So right now she's not exposed. However, a potential dangerous situation arises when the RH negative mother has a first pregnancy with a RH positive baby. So in the first pregnancy, there are rarely problems because over here, problems rarely develop in a first pregnancy between an RH negative mother and an RH positive baby. So here you see the mother's blood is RH negative, the baby's blood is RH positive. And because fetal cells do not cross the bloodstream into the maternal bloodstream, then everything is good. Okay. During delivery, however, if there's hemorrhaging, bleeding, right, occurs, then there will be a mix of the fetal and maternal blood. And the baby's blood, the fetus's blood, will enter into maternal circulation, and that may cause some havoc. Okay. This can stimulate the mother's immune system, right? So once the mother gets exposed during hemorrhaging, during birth, right, she will produce these antibodies. She got primed, she got sensitized, and she will produce these maternal antibodies, okay? And that could be a problem in the next pregnancy. It's not a problem for her now, right? She's actually totally fine having these antibodies. She won't bind onto her own red blood cells. There's no antigen on RH negative, right? But now she has these antibodies. There's no problem at all. The problem comes during the second pregnancy. If this second baby is RH positive, right? Then the mother's RH, now she has these antibodies, right? That she made during the first birth. And now, as I told you, RH negative, right? The red blood cells do not cross onto the other side. However, these antibodies, they can cross the bloodstream and they could enter onto the other side. And so these antibodies could cause agglutination and hemolysis of the baby's red blood cells. Look, the second baby, if they are Rh positive, right, then the mom's antibodies cross because the mother does provide antibodies to the baby during their development for protection. So these would cross and they would bind to this and hemolyze those red blood cells. This would produce a dangerous anemia for the baby and it could cause the death of the baby. So a treatment for this second pregnancy would be special injections that prevent the Rh positive antibody production in the mother after the first pregnancy. So we would stop the production of these antibodies so that it won't go and attack. Interestingly, this is a little bit higher level. If you don't get this, this is okay. The opposite scenario doesn't happen. If the mother was Rh positive and the baby was Rh negative, that would be problematic, you would think, right? Because the baby would have this be affecting the mother and it could kill the mother. But that doesn't happen because babies don't start making their own antibodies until year 1. So actually this is not a problem. Babies don't make antibodies, so they would never cross the placenta. They would never cross into the mother's tissue, into their blood supply, and so that's avoided. Okay, so again, here is like a little sheet that helps to organize everything, right? Next thing is platelets and hemostasis. So what is a platelet? A platelet is also called a thrombocyte. So I need you to know thrombocytes are platelets. It's another name for platelets. And they are cell fragments. They're not full cells, right? Here you see this big cell, this megakaryocyte. It gets broken down into these smaller pieces. You break pieces off of this and it becomes platelets. They do not have a nucleus. I do not see any of these platelets have a dot in the middle. And they just contain some cytoplasm. And with clotting proteins, they help stop bleeding in damaged blood vessels. I need you to know this. The function of platelets is to clot and stop bleeding of vessels, right? So it's, sorry, not to clot, but to stop the bleeding in damaged vessels, okay? Where do platelets come from? They are made in the bone marrow. Here, remember we talked about the hematopoietic stem cells, right? These are in the red bone marrow, and they're part of the myeloid lineage, and they will transform. Remember the fate of the cell? I told you that this cell says I could become whatever I want, right? And then slowly the fate of the cell becomes this megakaryocyte, this big humongous cell, and this weird thing that I I feel like I've seen this in Stranger Things. This big weird megakaryocyte will a mega site, a mega cell will break into small fragments, right? Little platelets, right? And this will be used to clot. Okay, we're going to see how it's used in the clotting process. So how is thrombopoiesis controlled? Thrombo means platelets. Poiesis means production. So how is the production of platelets controlled? It's controlled by a hormone called thrombopoietin. Thrombo, right, means, again, platelet, poietin. Remember erythropoietin, EPO? Erythropoietin was a red blood cell, poietin production, right? It was a hormone that told us to make red blood cells. This was secreted by the kidneys. Thrombopoietin is a hormone that tells the platelets to make more of them, right? It's produced by the liver and kidney, and it will tell these cells to make more platelets. So TPO, or thrombopoietin, is released when there are low amounts of platelets, right? So this is called thrombocytopenia. Penia means small amounts, right? So when there are small amounts of thrombocytes, small amounts of platelets. Platelets, they get degraded over and over, right? So these don't stay circulating around, they get degraded, recycled, so we do eventually need to make more during our day, during our week. But also, TPO is released from the liver and kidneys when there's an increase in demand for platelets. So let's say there's inflammation in your body or an injury, right? And there's damage. Then TPO will be released to say, hey, you better make more platelets because you've got some repairs to do in the blood vessels, right? So, how are platelets removed from the circulation? 1/3 of platelets in the body are actually stored in the spleen. So, this weird, stupid organ that we've talked about that I really was like, well, we don't care about it that much. It's on the side of the body. In the lab, it's this purplish organ. 1/3 of platelets, they're actually stored in this spleen rather than in the bloodstream. We don't want platelets circulating around in the bloodstream too much during regular scenarios, or else they'll clot and they'll do bad things. So we actually go and we stick them in the spleen on reserve, and we wait until we mobilize them for when there's something severe, like severe bleeding that happens, then we'll shove them all out from the spleen. So they're on backup duty, waiting in the spleen. Platelets, they'll circulate for 9 to 12 days, and then they're actually going to be removed by the spleen and they'll be recycled and broken down. So, yeah, they're not, remember, they don't have a nucleus, so they can't fix themselves, they can't divide, so they get brought back to the spleen. So, what is the function of platelets? The functions of platelets is for hemostasis. What is hemostasis? Hemo means blood, like Hema Quebec, right? Blood, hema. Hemostasis. Stasis means still, to stay still, static, stop, right? To stay in place. So what for the blood to stop bleeding, right? So platelets cause hemostasis, which is the process whereby bleeding is stopped, right? So it occurs over three main steps. First, the vascular spasm. So the vessel itself actually starts squeezing and spasming like a muscle spasm. Second, the platelet plug formation. So there's a plug, a temporary plug that's made. And then the third step is called coagulation. This is the true blood clotting that occurs, okay? The fix in the wall. And then we heal and we retract the clot. The clot is kind of, if a dam breaks, right? They'll put up two walls on the side to try to fix, to temporarily block the wall, but then they'll rebuild the wall, right? And then they could remove the two temporary walls that they put up, okay? So here's my so eventually hemostasis ends when anticoagulant compounds, anti-clotting factors, right? They will overwhelm the clotting factors, and they're gonna be able to prevent the clot from continuing. All right. So, what do we have? Step one is of hemostasis, of stopping the blood. It's vascular spasm. This is an immediate effect, a contraction of the damaged blood vessel. Do you see the blood vessel here? It contracts and it gets smaller. It vasoconstricts. That will reduce blood loss. Remember, we talked about the fact that when you vasoconstrict, you will reduce the flow of blood, right? So it's initiated by chemicals released by the damaged endothelial cells of the vessel, and they will become sticky as chemical factors like serotonin and histamine, they're going to be secreted to attract platelets. So these little parts of the wall will attract platelets. They're sticky, and the contraction continues for about 30 minutes to buy sufficient time for the next two steps of hemostasis to occur. All right. So step 2 is the platelet plug formation. Platelets stick to the endothelial walls and they'll swell and release chemical factors. So over here you see that the platelets, they stick to the endothelial wall here and they'll swell. You see that here it's swelling and they release these chemical factors. And these chemical factors here, they will cause even more platelets to come and aggregate 15 seconds after injury. And then more platelets will come, right? And eventually they will form this platelet plug. I need you to understand this is a positive feedback loop. A negative feedback loop is that, you have a stimulus, right? Let's say the platelets started to accumulate and you would try to decrease the platelets, counter it. But this is not the case. We have a positive feedback loop here. Some platelets aggregated. This caused the attraction of more platelets. All of those platelets release factors that cause the attraction of even more platelets. So that's called the positive feedback loop because it's amplifying the stimulus, right? The stimulus is getting amplified bigger and bigger and bigger. And the last step is this coagulation blood clotting. So, this looks like a shit show. There are many things here you do not need to know, and we've cut stuff down. But this is very cool. Look at how the clotting actually, this is a real picture under a microscope of the red blood cells all forming this. You see the red blood cells stuck in this mesh over here, right? This is the net, the clot that's occurring. So coagulation, this is another word for blood clotting together. It reinforces the unstable platelet plug. This thing here was not stable. It was kind of just a temporary fix, but it would, as I said, you need to actually the clotting process to occur. So the platelet plug is there, but it's unstable, and coagulation will actually cause the gelatinizing of liquid blood. Have you ever had a cut or you've scraped off some kind of I forget the word in English. When you have a little, I don't know what I'm talking about. A little scar and you pick off the scar and then all of a sudden you watch, it's bleeding, you patch it up and then you see that there's this little jelly like blood that forms eventually once it stops bleeding, right? It's like this very thin layer, but it's jelly-like, and of course, if you touch it too much, it'll keep bleeding. But there's this like kind of layer of gelatinized liquid, right? That's what clotting is. That's blood coagulation. It's key to know that this process only starts 30 seconds after injury. So thank goodness we had the vascular spasm to reduce flow of blood. We had the platelet plug so that we could form a temporary plug. And then after that, so once this occurs, the damage of the connective tissue and the basement membrane, this will cause one protein to activate another protein, to activate another one, to activate another one, to activate another one, to activate another protein, etc., etc. So it's a protein cascade. It's a very complex enzyme cascade that I don't need you to know about. And what I do need you to know about, though, is that for this cascade to occur, right, you have many clotting proteins. These are called clotting factors. So do you see this tissue factor 3, tissue factor X? All of these will feed into the loop-de-doop, and eventually they will form the clot over here. You see there's one loop here, and then it forms the clotting over here. You have another loop here that forms the clotting over here. And I need you to know that to kind of the cascade involves clotting proteins, and these are made by the liver. So actually, if you have cirrhosis or liver damage, then you'll probably also have difficulties with clotting. Okay. So these clotting factors, you also need calcium. Do you see how calcium feeds into this? So it's important to have calcium, and vitamin K is important in clotting too. So instead of memorizing this whole pathway, please do not even try. Don't put it on your memory aid. What I want you to understand is that there's two pathways. The extrinsic pathway that leads to clotting, and then there's another pathway, the intrinsic, right, that leads to clotting. And both the extrinsic and the intrinsic, eventually they feed into a common pathway, which will cause the clotting. So, what is the extrinsic pathway? More generally, exposure to underlying connective tissue. It's extrinsic, right? It's the outer part, this connective tissue on the outside of the blood vessel. When that's ripped, right, that will trigger the extrinsic path in the plasma. Okay? So it will cause this factor to do that, blah, blah, blah. The intrinsic pathway is if you have damage to endothelial cells. Do you see the inner endothelial cells that are going to be on the inside? That breakage would cause the intrinsic pathway, right? Because there's exposed basement membrane of the vessel, that intrinsic path would be activated. And the truth is, both of them are usually going on at the same time, but both of them feed into this common pathway, and they activate this factor 10, right? This clotting factor 10. And this will positively reinforce a common pathway. Here you have goes down. And the only step I really need you to understand, so you need to understand that there's these two pathways that feed into the common one. But what I need you to the only factors I'll ask you to really understand is that this factor 10 feeds in and it will convert. I need you to understand this last step very well. It will convert fibrinogen into fibrin. Okay? Please go back to your blood lecture, your other blood lecture. Fibrinogen is a plasma protein, right? Fibrinogen, let me remind you, in your blood vessel, right? Here's your blood vessel. You have some red blood cells over here, right? And in between, in the plasma, you have some fibrinogen. And you will recall, go look at the notes, fibrinogen is soluble, meaning it mixes well with the water, right? Well, if I have a little break, let's say over here, right? Let's say at this point, I break my vessel, right? My blood vessel breaks over here. This fibrinogen will bind over here, and the factors, right? All of this intrinsic and extrinsic pathway will convert fibrinogen into fibrin. And what is fibrin? Fibrin is a bunch of fibrinogens cross-linked together. They become insoluble. They stop being able to float in the water, and they actually clot together and form this little mesh of fibrin. So that's the step that I need you to understand here. The fibrinogen, which is usually okay, will, if activated, it will clot together and form this mesh where the vessel is broken. This is the mesh of fibrin altogether. The last thing here is dysregulation of clotting. What happens if we have low amounts of this clotting ability? This is called hemophilia. Remember, hemostasis means the stalling of blood. Hemophilia means philia means to like, right? To increase, right? So you increase the amount of blood, you like the blood that's coming out, you're not stasing, you're not stalling it, it keeps going, right? So hemophilia is a genetic disorder, due to inadequate clotting factor production. Usually it's this factor 10 that is not produced enough. It is linked to the X chromosome, so it is actually more common in males. And the cause of hemophilia, oh, sorry, I said the wrong thing. The cause of hemophilia is usually this factor over here, factor 9. Sorry, this is factor 8. I still can't do Roman numerals. Of the intrinsic pathway. So if we go look at this intrinsic pathway over here, it's actually this one that's usually affected. And so the treatment to this, right? Wait a minute. What is hemophilia? These people, right, will bleed nonstop. They will bleed to death, actually, if they do not get an injection of clotting factors. There are coagulants that you could give to help clot things, right? There are anticoagulants you could give if you want to so anticoagulants will stop clotting, and coagulants will try to increase clotting, right? In these patients, the severity of their disease depends on how much clotting factor production is affected, right? If it's a major clotting factor, then that's not good, but it could be a less severe one, and the treatment would be transfusions of these missing factors would be given, right? So here you actually have the thrombocytes, you have these platelets, and they will, remember, the platelets usually stick to the sides. And then eventually, the coagulation factors, remember, they're the ones that allow you to clot, right? Without coagulation factors, pretend that they're not there, right? The platelets will still clot, but then you will not be fixing that clot with the whole, with all the clotting factors, right? You will not be able to do that, and so you get hemophilia. The wound doesn't clot, and you bleed and bleed and bleed, right? And if this is a big rip, then that will definitely happen. The platelet plug can still form, but you actually can't do the actual clotting, the coagulation, right? So make sure you understand the 3 steps well. The last thing to look at is leukocytes. I think always of leukemia, and cytes is the cells. So I know that leukemia is due to white blood cells, so leukocytes are white blood cells. What are the characteristics of leukocytes, of white blood cells? Leukocytes have immunological properties and defend against pathogens. You're going to have an entire course on this, so I'm not going to spend a lot of time. But leukocytes, I need you to know that unlike red blood cells and unlike platelets, white blood cells, they have a nucleus and they have organelles. Look at them. They have a big nuclei. It looks weird. It's not a nice round. It's actually lobed. And they have organelles. Do you see the little dots everywhere? So another thing I need you to know is they're found in low amounts. Do you remember doing your blood smear when you smeared your blood in the lab and you saw under the microscope there was many thousands of little red blood cells, but for every thousands of red blood cells there was like one big purple one, and you're like, oh, look, there's a white blood cell, and then every now and then, oh, another white blood cell, right? So they're actually found in low amounts compared to the red blood cells. Every 1 for 1,000 red blood cells. Where are white blood cells found? Unlike red blood cells, this is key. Red blood cells always stay in the blood vessel, right? Unless shit hits the fan. White blood cells are not confined. When we breach in the barrier, let's say we break in the barrier, that will cause bruising because red blood cells go out in the plasma, right? But if our blood vessels are intact, then we're actually okay, and our red blood cells should stay, I'll put a red blood cell here, it should stay in the circulation and not exit, right? So they're confined to the red blood cell, whereas white blood cells are not confined. Look at them. These little guys creep along the blood vessels and they go where needed. they will exit into the interstitial space, and they'll go wherever they need to. During injury or during infection, let's say there's injury or there's infection and bad bacteria over here, white blood cells will migrate out of the vessel. This process of migrating out, do you see how it squeezes here? That's called diapedesis, okay? That's the process of them exiting the blood vessel into the connective tissue at the sites of infection or damage. So white blood cells are attracted to specific chemicals at the site of injury or infection. This is trying to show you the injury or infection at this area, okay? I love this video. Okay, let me wait until it restarts. So here you see a nice little, this is the inside of the red blood vessel, and you see the white blood cell go, and diapedesis was the squeezing through over here. The white blood cell squeezed in, that's diapedesis, and then it gets attracted to the chemicals that are over here. So maybe this is chemicals from bacteria, right? So they get attracted. Chemo means chemicals. Taxis means to be attracted to that region. It will undergo chemotaxis and get attracted to them. Okay? So that's how white blood cells know where to go. Thank goodness they know where to go, right? How are white blood cells classified? Leukocytes are broadly categorized into two groups. We have the granulocytes. Granulocytes contain large secretory vesicles in their cytoplasm. Look at all these little dots here, right? Those are secretory vesicles, and you'll actually see them under the microscope. So do you see how these ones don't have the little dots? Or, sorry, they don't have as many of those little dots, right? So those are agranulocytes. When you have avascular, all of these words with a in front of it, aneural, that means you do not have avascular, no vessels. Agranulocytes means no granules, right? So they don't have granules. So they contain few to no cytoplasmic granules. So here we have the neutrophils, eosinophils, and basophils. And here we have the monocytes and the lymphocytes, okay? So all the phils are granulocytes. Let's look at those phils. That's not a true scientific term. Neutrophils, they make up, this is the one that I told you would see under the microscope, most likely, because it's 50 to 70% of the white blood cells are these guys. They are dense, segmented, multi-lobed nuclei. Do you see how there's more than one lobe? 1, 2, 3, 1, 2, 3. There's more than one lobe. That's a neutrophil. They're part of the innate immune system. They're part of the non-specific branch, and they usually are the first responders to infection or damage. They are the ones that quickly go to the location where there's some damage, and they are highly mobile, and they are phagocytic. Phago means to eat, cytic means cells. So they have the ability to eat cells. They eat bad bacteria, they eat bad things that are around. Eosinophils, these are the bilobed nuclei. Do you see how there's two lobes in the nuclei? They are stained dark red with acidic dyes. They are part of the innate immune system, the non-specific branch, and they are specialized in killing large multicellular parasites. So, again, they're circulating around ready to find these bad parasites. They are phagocytic too. They will eat the parasites, so they are phagocytes. They eat cells, right? Basophils, oh, these assholes, are only about less than 2% of white blood cells. They're bilobed. You don't even see the lobe here because it's such stained with these little granules, right? This is part of the innate immune system. These stupid granules here are histamines because these cells, they are the mediators of allergic reactions. They're there and they will cause allergies. They release the histamine. All these granules are stupid histamine that give you your allergic reaction. That's why when you're sick, you will take an antihistamine to try to stop. You're never going to cure your allergies, but when you have a bad reaction, you will stop the histamine from affecting you. They'll accumulate and damage tissue too. Agranulocytes, these are 4 to 8% are these big monocytes. There's a kidney shape here. Part of the innate immune system as well, the non-specific branch, they will circulate for about 24 hours, right? And then they enter the tissues and become tissue macrophages. So a macrophage is another phage means to eat. They are big eaters, macrophage, right? They are phagocytic and they release chemicals to attract the neutrophils and the monocytes. They can also attract fibroblasts to form scarred tissue, and they commonly associate with chronic infections. You might have heard of mononucleosis, right? So mono is usually you will have a high amount of these monocytes. And when you have a lot of recurring infections, it makes you very tired. So that's why mononucleosis is it will make you extremely fatigued. The last one, and this is another one I really cared about, remember the neutrophils, because these were very prevalent in our blood. And also I told you to look out for our lymphocytes. This makes up 20 to 40% of our white blood cells, right? So lymphocytes, look at them. The rounded nucleus almost dominates the entire cell, but you see a bit of cytoplasm here. It's part of the adaptive immune system, the very specific branch. So it exists between our circulatory and lymphatic system, and there exist three types of lymphocytes. You have T cells, B cells, and natural killer cell, NK cells. T cells destroy virus that are infected, virus infected cells. So when you have a viruses hijack your cells and they will dominate and hijack your own cells. So T cells will actually go and kill your cells that got infected. B cells produce antibodies. So these are the cells that make the weapons, the antibodies that attack foreign bodies, right? So the B cells, remember the antibodies that I told you for the blood typing? Well, the B cells, those make some antibodies, okay? And NK cells, they survey the immune system. They target any abnormal cells, especially cancerous cells. They will stop cancers from arising. So, how do T cells know what to attack? It's due to antigen presentation. This is a process, you know what? Forget about this. This is too much detail. Just go and X this out. You don't need to know this. But basically, just for funsies, your body looks at the markers on your, and when it's a self marker, the immune system won't attack it. If it's a marker that is not yourself, it will attack it. And that's why the red blood cells, right? If they had a marker like the A antigen or the B, then the white blood cells or the antibodies will not attack it. But if it is a marker that it doesn't like, it will go and attack that, right? Nobody cares. Abnormal leukocyte numbers. Remember, I talked about the fact that, uh, in thrombocytes, we could have too much or too little. Actually, let me review something. For red blood cells, what is it that when we have too little red blood cell, what is that called? That's called anemia, right? If we have too much, it's called polycythemia. If we have too little thrombocytes, it's called thrombocytopenia, right? Um, And if we have too much, it's actually called thrombocytosis. Um, if we have too low amounts of white blood cells, this is called leukopenia. Remember, penia means low. So where do we see leukopenia? Um, this is when you have a weakened immune system, right? Patients who have HIV or AIDS, or patients who have these chronic infections that are beating up their immune system, right? If you're taking some meds that diminish your immune system, right, then you will have leukopenia, all right? Um, so that's low amounts of white blood cells. Interestingly, in HIV and AIDS, here you see a little virus that's going to affect your T cells. They actually infect your T cells and degrade your T cells. Um, Over here, high levels of white blood cells. If you have too much white blood cells, this could occur due to two things. Maybe during an infection, you will try to increase your white blood cells to try to fight something off. So, oftentimes during infections, if you have COVID, if you have a cold, your white blood cell numbers will be increased, and then once you've fought the infection, your white blood cell numbers will decrease. This is a white blood cell chasing a little bacteria. It's kind of crazy. Leukemias, they are also a situation where you'll have high white blood cells. Actually, leukemia is like cancer, right? This is a type of cancer where you have unregulated white blood cell division, right? You never hear about erythrocemia, right? You never heard about red blood cell cancers that much because they don't have a nucleus when they're in circulation, so they can't divide. Cancer is the uncontrolled division. So if you don't have a nucleus, well, you won't be able to undergo this cancer process because you don't even divide in the first place, right? So it's quite rare to have red blood cell cancers. It's also quite rare to have thrombocytic cancers, platelet cancers, because they don't have a nucleus either, right? Okay. This was just for funsies. I want to prove to you that what we taught you is quite useful. Um, so when you do a blood test, right, what is it that they're testing? Often they'll see the white blood cell numbers, the red blood cell numbers. They will look at your hemoglobin levels in grams per liter. They will look at your HCT, your hematocrit. They will look at your mean corpuscular volume. We didn't talk about this, but this is the size of the red blood cells. Their mean corpuscular hemoglobin, how much hemoglobin. This is important to know if you're making enough hemoglobin. Maybe during iron deficiency anemia, you wouldn't. Red blood cell width, platelets, mean platelet volume, neutrophil, basophil, blah, 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 right? Reticulocytes are those precursor red blood cells. You don't need to know this slide, but I thought it was cool to just prove to you that I'm not teaching you bullshit. Okay, take it easy, guys. That's all I have for now.